VA back with another lab video. This one's on oscillations. The introduction. The purpose of our lab was to investigate the motion of a spring mass system with the mass oscillating in an arc. I used Tracker to track the motion of a mass on a spring, provided in a video. I used GlowScript to create a computational model of my findings and test if it was accurate. We can find that this model is accurate as the total energy change of the system remains at 0. Also, quick shout out, Game 1 of the World Series, Yankees versus Dodgers. Shout out to the Yankees. Cheer for them. Let's go. Fundamental physics principles. Newton's second law. Net force is equal to spring force and the weight force. This will be useful in our GlowScript code, and it's also very useful to understand. Because we can see, we can talk about the net force and how it affects the mass and its movements. The energy principle provides that the total system energy is equal to the work from the surroundings and the Q. The work from the surroundings is in the isolated system should be 0, which means that the total system energy change is equal to 0. Some useful formulas used in the GlowScript are velocity update, position update, kinetic energy, gravitational potential energy, and spring potential energy. We will see these all in the GlowScript. My tracker observations provided some initial conditions for you to read. From my calculations, I found that the spring stretch initial was 0.7 meters, the length of the spring initially was 0.123 meters, and the spring constant was 6.82 newtons per meter. The initial position and velocity were as provided, and the initial velocity is 0 as the mass started at rest. Here you can see a plot of the position versus time graphs of the x coordinates and the y coordinates of the mass. Some of my GlowScript input. On the leftmost image, we can see the energy formulas put into code, and we can see the calculation loop relating to my time of the video recording. The initial energies are obviously equal to the energies that we've described before. All the formulas for gravitational, spring force, and the net force, as I described in the fundamental principles slide. And we have the velocity update formula, position update formula, and the spring update position. Now we see just some inputs on the right side, the mass of the system, initial conditions, and the gravitational constant, spring constant, relaxed length of the spring, and all those formulas. We can see the energy iteration by just adding the new k to the initial k, which is defined before. My computational findings are pretty similar to what I found in my graphs, and this is pretty nice because it shows that the model does indeed work. Some sources of error could be that the system in the video was truly non-isolated, as it is very hard to maintain that in real life. Another error could be my fault, as I could have inaccurately tracked the mass on my screen in the software. Is the energy principle satisfied? The big question of this lab. I would have to say it is, because we can see that the change in energy versus time graph, it's a little weird to understand, but because there's no change in the orange line, that means that the change in energy is 0. And if you want some more proof, we can see that the total energy, if you add all of these bars up, it does equal 0. So yes, the energy principle in my computational model is satisfied. Oscillation periods from both directions. What I did here is I took 2 peaks from the x position versus time graph and from the y graph, and I took 3 and I averaged the distance between 2 of them, and then I averaged it. So in the x direction, we have a period of 1.65 seconds, and in the y direction, we have a period of 1.475 seconds. Because the spring constant formula is related to the the period of the spring oscillation, we can see that these different values would lead to different spring constants and therefore different graphs. Again, thank you for listening. If you're a Yankees fan, I love you. Good luck to the Yankees. I'll see you next time.